Hello, my name is Andrew, and this is my Physics 2212 Lines of Charge lab. This lab analyzes the interaction between two charge tape pieces, and in this lab I create a computational model to simulate the observed interaction between these pieces. The purpose is to determine the approximate magnitude charge on one piece of charged clear tape using our knowledge on electrical force, electric fields, and charges. It's also to analyze the interaction using a model that evenly distributes the charge across the length of the tape and compare the results to the results from a model that treats the charges as point charges. The main result of this lab is that the tape had a positive charge of 1.24 to the negative eighth power coulombs, which was a slight decrease from the lab 1 result of 1.307 to the negative eighth coulombs. The formulas that I used in this lab include Coulomb's law, the electric field formula, the gravitational force formula, Newton's second law, and another version of Coulomb's law where electric force is equal to electric field times charge. And in these first two laws, the K is equal to 9 to the ninth. The concept that makes this lab different than lab 1 is electric field superposition, which is splitting up the length of a charged object into many small segments that act as point charges and then adding up the electric fields that they have on each other. And like the last lab, like charges repel and opposite charges attract. So the initial conditions of this lab is that the tape starts out neutral, but by pulling it off of the base tape, it becomes charged, and that charge that it gets from pulling it off is positive, which was tested in the last lab by putting positive and negative objects and neutral objects next to it and seeing that it repelled other positive objects and attracted negative objects. Length of the tape was 0.2 meters, weight was 0.2 grams. The system is tape B, and the surroundings are tape A and the earth. Some of the assumptions of this lab is that the charge is equally distributed along the pieces of the tape, and each piece of tape has an equal charge. And the other assumption is that air resistance can be ignored. When I held tape A under tape B, I found that the distance between the two tapes was 0.028 meters, and this interaction can be represented by this model here with the 6 red circles and 6 blue circles. The red circles representing tape B, the blue circles representing tape A. Tape A has an electric force on tape B that's directed upwards, and tape B has gravitational force acting downwards on it. And since tape B is not moving, we know that these two forces are equal in magnitude. And this model is represented by several circles rather than just one because it's represented as a line charge rather than a point charge. And each circle represents a segment of the tape. And since we can determine gravitational force by mass times gravitational acceleration, and we know that's equal to the electric force, we can use this formula, plug in what we got for the gravitational force, and isolate Q on this side of the formula. And by doing so, we find that the force is 1.24 to the negative eighth coulombs. So moving on to the computational model, we can see here, this is K, 9 to the ninth power, the gravitational constant, the mass of the tape. The charge here, this is a charge that I calculated in the previous slide, and I had to multiply this number in order for it to be equal to the gravitational force. Here's the tape length and the distance between the two tapes here. And this function is how we calculate the electric field of the particles, which we can see is the same as this equation here on the left, as E equals KQ divided by the magnitude of R squared times R hat. And here shows the line of charge function. Down here is the two tape objects, including their position, axis, mass, and charge, and color. And back to the line of charge function, N here represents how many points we're representing the line charge with, or how many segments we're cutting the charged object into. And here we can see the for loops for the electrical fields at each of the segments and how they interact on the top tape and the bottom tape segments. And this bottom code here creates the arrows for gravitational force and electric force. So that computational model is displayed here with the blue line here being tape A, the red line here being tape B, the green arrows being the electrical field, and then the big white arrow being the electric force, and the yellow arrow being the gravitational force acting downwards. And you can see that the electrical force and the gravitational force have the same magnitude. So we found through the computational model that the electrical and gravitational forces had the same values for both the computational and observed models. The computational model was only 0.002 off of the observed calculations. The computational model and my calculations use the same method to determine charge and force, which is why they're so close. And some possible sources of error are related to the assumptions that we made earlier in this lab, which include that charges are not perfectly equally distributed along each piece of the tape. We also assume that each piece of tape had the exact same charge, whereas some charge may have been lost due to my hand while handling the tape. And we also have to account that the pieces of tape are divided into finite segments, which are still not a perfect representation of its charge. 1.24 to the negative eighth coulomb makes sense as a charge acting upwards on tape B because we determined that both pieces of the tape become positively charged after being pulled off the table quickly. Two positively charged objects repel, which causes tape A to go upwards. So what if I had modeled each of the tapes as a single point charge, like in the previous lab? Well, using data from lab 1, where the charges from tape A and tape tape B were treated as point charges, we found that the charge of each piece of tape was 1.307 to the -8 coulomb, whereas in this lab it's 1.24 to the -8 coulombs. So these are pretty similar, it's just a small 5.1% decrease. We can assume Lab 2 is more accurate though, because it models the charges being distributed along the piece of tape, which is more accurate to reality. And this line charge model considers the interactions of many segments along the pieces of tape, and some of these interactions determine the net electric charge, whereas the point charge model in Lab 1 only considers 2 charges. Thank you for watching my lab.